So, in the last class I have discussed about the settlement calculation of clay soil and the granular soil, and then I discussed about the plate load test and how this test is conducted, then what are the correlations of the plate and the real foundation in terms of settlement and the bearing capacity for granular soil as well as the clay soil. Now, today I will solve a problem on the plate load test. So, this is the example A, the first example that I am talking about, that following data was obtained from a plate load test conducted on 60 centimeter square plate. So, the plate size which is 60 centimeter, and the plate load test is conducted at a depth of 2 meter below the ground level on a sandy soil. So, which extend up to a large depth. So, that means the homogeneous soil. So, determine the settlement of a foundation of 4 cross 4. So, 4 meter cross 4 meter carrying a load of 1200 kilonewton placed at a depth of 2 meter below the ground surface on the same soil. So, that means here the depth of foundation and depth of plate both are same. So, we do not need to apply any corrections. So, now what will be the actual settlement if water table is raised at the base of the footing. So, initially in the example A there is no water table effect, but in the example B if the water table is raised at the base of the footing, then what would be the actual settlement. So, that means the real foundation is 4 by 4 and the load is acting at 1200 kilonewton. So, what will be the settlement of the foundation. So, this is the load intensity in terms of kilonewton per meter square, and this is the settlement. So, this load is applied, this settlement is measured at the end. So, that means here, so for the each load increment. So, first one is 50, then the 100, then 150. So, this is the 50 increment for 200, 250, 300, 350 and 400. So, there may be, so your safe load that you have calculated is 250 kilonewton. So, you are applying 1/5 of that. So, first one is the 1/5 means the 50 kilonewton, second one is the 2/5 that means the 100 kilonewton, like that. So, and this is up to the failure of the loading. So, or up to the up to the required settlement that I have discussed in the last class. So, here this is up to 400 kilonewton per meter square. So, that means here it is the incremental load is 50 kilonewton per meter square, and this is the corresponding settlement. So, what we are doing, the first it is plotted. So, this is the x axis is the load, x axis is the load or the stress that you are applying. So, it is in terms of kilonewton per meter square. This is the x axis, and the y axis is the settlement in millimeter. So, this is the y axis. So, and this is the settlement, and this total thing is plotted. So, this is the load settlement curve, load versus settlement curve. So, now the load intensity, the total area of the footing is 4 cross 4. So, that is the 16 meter square, and the load is load P is 1200 kilonewton. So, the load intensity is equal to 1200 divided by 16. So, this is 75 kilonewton per meter square. So, now the 75 kilonewton per meter square. So, this is each line is representing 20 kilonewton per meter square. So, 75 will be, this is 20, 40, 60. So, it will be around here. So, this is the 75, this is 75 kilonewton meter square, and this is this axis is basically the settlement axis in millimeter. So, corresponding settlement of the plate, this is the SP settlement of the plate is 4 millimeter. So, from the chart, the corresponding to 75 kilonewton per meter square, the SP settlement of the plate is equal to 4 millimeter from the curve. So, now the settlement of the foundation that I want to calculate. So, if I use this correlation SP BP BF into BP plus 30 divided by BP BF plus 30. So, this is whole square. So, now if I put these values, the SP is 4, then BF, this is the width of the footing is 400 because it is in centimeter. So, 400, width of the plate is 60 plus 30. So, divided by 60, 400 plus 30. So, this is whole square. So, the settlement of the plate, settlement of the foundation is coming out to be 7.8 millimeter. So, this is the answer for the part A. So, that means corresponding to 1200 kilonewton, the settlement of the foundation will be 7.8 millimeter. Now, this is the part A. Now, the part B. So, our actual settlement is equal to the settlement and the CW. CW is the correction factor. So, as the correction factor, that means I have mentioned that we have two corrections factor that we can use. Now, if I use the IS 8009 method, then my CW value will be 0.5 plus 0.5 into 0, because here as per this IS code method. So, this is your dW dash is measured from here, because this is the expression is 0.5 plus 0.5 into dW dash divided by B. So, here your B value is equal to 4 meter. So, B value is 4 meter, but DF value is measured from the base and the water table is at the base. So, your DF dash is 0, that is dW dash or dW dash is equal to 0. So, dW dash is equal to 0 means the CW is 0.5. So, for the IS code, this is 7.8 divided by 0.5. So, that will be equal to 15.6 millimeter. So, this is 15.6 millimeter is the actual settlement, your CW value is 0.5. Now, if I use the another method, that is the Peck, Hansen and Thorburn, (1974). In their case, CW is equal to 0.5 plus 0.5 dW dF plus B. So, here dW will be the base of the footing and the dW basically this is here the base of the footing, means here the dW is measured from the surface. So, and this is the position of the water table. So, your dW is equal to 2 meter and dF value is also 2 meter and B value is 4 meter. So, in that case CW value is 0.5, 0.5, dW is 2 divided by 2 plus 3, 4. So, because it is B value is 4 meter. So, it is 4. So, that means here this value is 0.67. So, actual settlement will be 7.8 divided by 0.67. So, it is 11.64 millimeter. So, if I use the IS code always give a higher settlement if I use apply the water table correction, because here from the base to the surface always it is 0.5, but in other methods will give you slightly lower settlement value. Similarly, IS code will give you lower shape bearing capacity, and the other method will give you slightly higher lower shape bearing capacity value. So, this is the two methods that I have discussed for this problem. So, now the next problem A. So, if I use the same plate load test data and determine the allowable bearing capacity of a foundation. So, remember that here I want to determine the allowable bearing capacity. Okay, so, what is allowable bearing capacity? Allowable bearing capacity definition as given, the maximum load it can take in terms of bearing capacity or shape bearing capacity, and the maximum load it can take in terms of settlement criteria, and minimum of these two will give me the allowable bearing capacity. So, previous problem where there is a particular load on a foundation. Now, corresponding to that load, what would be the settlement? And then if the water table effect is there, then what would be the settlement? But here the problem is that we have a foundation, or that the foundation width is square footing, again 3 cross 3, and depth of foundation is 2 meter, and the settlement, and there is a permissible settlement of the foundation is 50 millimeter, and factor of safety against bearing capacity is 2.5. Unit weight of the soil is 19 kilonewton per meter square. So, here now we have to calculate the allowable bearing capacity. So, as there is two criteria, first criteria will check the bearing capacity and the second criteria will check the settlement. So, one is bearing capacity criteria and one is settlement criteria. So, we have a permissible settlement. So, we are using both two criterias, and then we will find what would be the allowable bearing capacity. Okay. So, first let me do the first criteria is the bearing capacity or the bearing. So, we are taking the bearing capacity criteria, and as I mentioned, in the bearing capacity you have to apply the factor of safety, and that is 2.5. And in case of settlement, we have to no factor of safety we apply, but there is a permissible settlement, and that is 50 millimeter. That means you have to design your foundation such that the settlement should not be more than this permissible settlement. Here it is 50 millimeter. So, first bearing capacity calculation. So, this is the chart. So, now if I draw, because there is no particular peak. So, this is the curve. So, again this is the settlement, which is millimeter, and this is the load in kilonewton per meter square or stress, this x axis. So, now if I draw a double tangent, so this is the initial state portion of the curve, this is the final state portion of the curve. So, this is the intersection point. So, corresponding value is coming out to be, this is 254 kilonewton per meter square. So, this is 220, 40, this is 254. So, from the chart. So, that means the QUP ultimate load is 254 kilonewton per meter square. So, this is the granular soil on the sand. So, now the QUF means the ultimate load for the foundation. This is for the foundation, this is for the plate. So, that will be QUP into BF divided by BP. So, 254, so footing is 3 meter divided by or 300 and divided by 60. This is 3 meter and this is 60 millimeter. So, 300 millimeter by 60. So, this value is 1270 kilonewton per meter square. So, remember that this is the ultimate load of the foundation. And one thing that I want to explain, that you can take this load and then divide it by the factor of safety, then you will get the safe load, that can act on the foundation in terms of bearing capacity. But one thing, that here the plate load test is conducted at the base of the foundation. So, this is the DF. So, that means this portion of soil is removed. So, we are not getting the resistance, or we are not getting the effect of this portion of soil. But when the construction will be there, so after placing the foundation, you will also feel this portion of soil. So, really in the real field, you will get the resistance or more capacity for this portion of the soil, and this portion of the soil is nothing but the surcharge Q. So, that means, we have the three effect. One is due to the cohesion, first term, second term is due to the surcharge, and third term is due to the weight of the soil or the friction. Okay. So, this surcharge term, second term effect, we will not getting from the plate load test data value, but in the real field you will get the resistance for the second term of the surcharge also. So, that means, indirectly I can calculate that value also. So, how I can calculate that value? So, how can I calculate that value? So, if I use the Tarzaki's bearing capacity expression. So, I know that Tarzaki's bearing capacity expression is your QU is CNC plus QNQ plus half B gamma N gamma. Now, here this part is 0 because your C value is 0, it is granular soil. So, now the contribution that I am getting is for this one, this 1270 kilonewton per meter square is this one, this is the 1270 kilonewton per meter square, because I am not getting this contribution, that I want to add. Now, here that means half B of the foundation, this is B of the foundation, gamma N gamma is equal to 1270. So, I can get the N gamma value from here, 1270 into 2 divided by BF, BF is 3 into gamma is 19, and this is a square footing. So, instead of half, so we will use 0.4. So, as it is a square footing, this is for the plane strain, this is for the strip footing. So, as this for the square footing, my QU is QNQ plus 0.4 B gamma N gamma. So, this is the actually 1270 kilonewton per meter square, because this is for the square footing, because this is the our 3 meter cross 3 meter plate. So, but this expression is applicable for the basic expression, which is applicable for the strip footing. So, actually this is not the 1270, the 1270 is this one. So, that is why NQ value instead of 0.5 we have to write 0.4. So, 0.4 BF gamma N gamma. So, that means this will be cancel out and this will be divided by this will be 0.4. So, this is NQ will be 1270 divided by 0.4, 19, and this is 3 the width of footing. So, this is NQ is coming out to be this value 55.7. So, from here my NQ value we are talking N gamma value is 55.7, but so I do not know what is the phi value, is not given. So, from here using this chart, if I calculate the phi value in the reverse way, generally these charts are developed corresponding to the phi. So, if I know the phi, you can develop this NQ, N gamma, NC, but here I know N gamma, I gain N gamma and I want to determine the phi value. So, this is the N gamma is here, N gamma is 55.7. So, it is in between 35 to 40 degrees. So, your phi value is in between 35 to 40 degrees. So, this is the range of the phi. Now, if your value is in between that, so we have to linearly interpolate this value. So, how we can linearly interpolate? This is phi minus 35, that will be equal to 40 minus 35 into 55.7 minus 42.4 divided by 100.4 minus 42.4. So, this value is coming out to be, this is 1.15. So, phi minus 35 degree is 1.15 degrees. So, phi value is equal to 36.2 degree. 36.15 36.2 degree, because we are just doing the linear interpolation, because this is your for 35 degree phi, the NQ N gamma value is 42.4, because for the 35 42.4, for 40 100.4. So, for 40 this value is 100.4. So, we are doing just linear interpolation, and our NQ value it is 42.4. So, this value is somewhere here. So, this is my NQ N gamma value, that is 55.7, and this is the phi that I want to determine. So, from here this phi value is coming out to be 36.2. So, if I do the linear interpolation, even in the other way also, if you have a phi in between that means 35 to 40, then NC, NQ, N gamma you have to determine by linear interpolation. So, once I get the phi value 36.2, so now corresponding NQ value from the chart is again, so this is 36.2 from the chart by linear interpolation I will get. So, that NQ value that I am getting is 51 from the chart. So, corresponding to for phi is equal to 36.2, and we are doing the linear interpolation the same way that I have done for the previous case. So, NQ value is 51. So, now NQ value is 51. So, that our Q N U ultimate. So, that will be Q N Q plus 0.4 B gamma N gamma. So, this is nothing but 1270. So, and then N Q I will get the unit weight into dF into N Q plus 1270, and unit weight is 19. dF is 2, because your depth of foundation is 2 meter. NQ I got 51 and plus 1270. And if I get this is ultimate, if I get net ultimate, then this is the NU ultimate, and if I get the net ultimate, then this will be the ultimate minus gamma dF. So, that we will get this is the net ultimate into 2 into 51 plus 1270 minus gamma is 19 into 2, dF is 2 meters. So, ultimately this value is 3170 kilonewton per meter square. So, the Q net safe, this is the Q net safe load is, or the safe load or safe bearing capacity or safe bearing pressure is 3170 divided by 2.5. So, this is the factor of safety 2.5. So, the load is 1268 kilonewton per meter square. So, in terms of bearing, if I apply the bearing capacity criteria, my safe load or the safe bearing pressure, this is the safe bearing pressure or capacity is 1268 kilonewton per meter square. So, it is in terms of bearing criteria. Now, we have to apply the settlement criteria. Now, if I apply the settlement criteria, so my permissible settlement for the foundation is 50 millimeter. So, this is the permissible settlement, or this is the so, I am designing my foundation for 50 millimeter settlement. Now, what would be the plate settlement corresponding to SF equal to 50. So, this is the SF, then this will be BP, then BF plus 30 divided by BF, BP plus 30. So, that is whole square. So, if I put 50, then BP is the width of the plate, then width of the foundation, this is 60 plus 30 whole square is equal to 27 millimeter. So, we are getting 27 millimeter is the settlement of the plate corresponding to the permissible settlement of 50 for the footing. Now, if I go back to that, if I go back to the load settlement curve. So, the SP is 27 millimeter. Now, this is the 27 millimeter around. So, corresponding Q is 320 kilonewton per meter square. So, the Q net ultimate or net allowable is equal to 320 kilonewton per meter square. So, this is in terms of settlement criteria and previous one in terms of bearing capacity criteria. So, the total, if I write this for the bearing, it is coming out to be, this value is coming out to be 1268 kilonewton per meter square, and for settlement it is 320 kilonewton per meter square. So, the minimum of this will be the Q allowable or net allowable. The Q allowable is be 320 kilonewton per meter square. So, Q allowable will be the 320 kilonewton per meter square, because that is the minimum. So, in terms of settlement that I are getting. So, here the settlement is giving the lower. So, that is basically the most of the cases we find that settlement terms will give you the lower bearing capacity. So, that is the lower bearing capacity or the Q allowable. This is the bearing in terms of net safe or the safe load carrying capacity in terms of bearing. Then in terms of settlement is 320 kilonewton per meter square. So, lower of these two or the smaller of these two, it will give you the allowable bearing capacity. So, that was the term A. Now, for the term B, if the water table effect is there, so definitely the water table effect is there. So, two way you can do it. So, one way you can take because your ultimate settlement is 50 millimeter. So, now if you apply the that is the actual settlement. So, your one way this your actual settlement is mint is equal to the settlement that you are getting from the plate. So, that is from the plate divided by CW. So, actual settlement is 50 millimeter. So, that means you multiply the CW with the actual settlement. So, you get the settlement from the T will be 50 into CW. So, and if as per the IS code, so that is why your settlement is, so your as per IS code IS 8009 method, the same thing, it is base of the foundation. So, your CW is equal to 0.5. If you use the other one, you will get the value. So, for the IS code is 0.5. So, your actual settlement from the plate will be your actual settlement into CW. So, actual settlement is 50 into CW. So, this will be 25 millimeter. So, you calculate the settlement corresponding to the 25 millimeter, and that definitely for the if it is 50 is 27, then for the SP corresponding to 25 millimeter, it will be 27 divided by 2, okay, 13.5 millimeter. So, corresponding to 13.5 millimeter, what would be the, so corresponding to your 13.5 millimeter, what would be the value? So, this value is 220. So, this will be, so Q allowable will be 220 kilonewton per meter square. So, that is 13 points. So, this is 220 kilonewton per meter square. So, this will be the 13.5. So, corresponding to 20 kilonewton per meter square. So, this way, because and I have applied the water table effect in the settlement only, because settlement is giving the lower value, that is why I have applied the settlement. Similarly, you can apply it for the bearing also, but bearing definitely will give you the more value. So, that is why I have not applied it in the bearing water table effect. So, I have applied in the settlement. So, you reduce the settlement and then the corresponding bearing pressure you can calculate. So, this way we can determine the Q allowable with the help of the plate load test data. So, and we have also introduced the water table effect, and then you will see there will be the reduction in the Q allowable value. So, in the next class I will discuss the other methods by which we can determine the settlement of the granular material or the foundation on the granular material. Thank you.